Hello, I'm Megan Dowell, and for my project, I created a chess artificial intelligence. The motivation for my AI specifically was to create an AI that human players at any level could play against, provided they already know the rules of chess. And for the behavior to be human-like, I didn't want it to feel like you were playing against an artificial intelligence, rather like you were playing against another person. I did not want it to be like AlphaZero, where the AI is sort of hyper-intelligent, competing with masters and always knows all the right moves, because while some people in the world can compete against them, those AI are not very human-like. So here's the problem definition. Firstly is the ability to predict opponent moves. So the AI should be able to think ahead a little bit and try to determine what the opponent would most likely play if the AI played a specific move. The second is different difficulty levels. The user should be able to choose easy, intermediate, or hard difficulties and have an increasingly more difficult time against the AI when going up each level. Third is the ability for both players to be AI and play against each other, so it would be able to run without human intervention, mostly for testing purposes. Fourth is minimize time to make decisions. So the player shouldn't be waiting 10 to 20 minutes for the AI to make a move. A few minutes is fine since human players do take time to think. They don't immediately make a decision, but the waiting time shouldn't be significant. And finally, higher difficulty AI should make better decisions than lower difficulty AI, so an AI on easy should lose frequently to higher difficulty AI. So there were a handful of challenges with this project, one of them being reasonable decision making. For example, moving the queen to a spot where it can be taken by an opponent's pawn would in general be an unreasonable move to make since the queen is worth much more than the pawn. Another one is the evaluation function. There are a few components that went into the overall value of each board configuration, but the weight of the different components like mobility and piece values was also a challenge. Next is how far ahead the AI should search for each difficulty level, like maybe depth 2 for easy, 4 for medium, 6 for hard, but determining what these numbers should be was a challenge. There's also the human-like decision-making issue. We don't want the AI to make a move completely out of left field. This is particularly hard to determine since for me, a beginner who learned chess 2 months ago, the AI may make a decision on hard that seems weird to me but may seem normal to a chess master. So in general, this would link back to the reasonable decision-making point. Lastly is limiting time to make a decision. With the base implementation of this, it was taking up to 10 or so minutes for an AI on easy to make a move when I was playing against it, which is far too long. So let's get into what was implemented to address these challenges. We'll review the approach for the AI, which includes book moves, sorting, an evaluation function, caching, and minimax with alpha-beta pruning. So when the AI needs to make a move, it first looks at the current board and uses a Python chess class called Polyglot to get the first book move from the performance bin file. If a move is found, that move is made and no further decision making is used. So when possible, the AI always makes book moves. If it cannot make a book move, the next step is to get all of the available moves, which is provided by the Python chess class. It then sorts all of the moves by estimating how helpful the move is to that player. So the value starts at 0 for the move, and then if the move can be an en passant capture, if it's castling, or if the move causes a check, the value is increased by 1 for each of those that are true. Additionally, if the move is a capture, then the value of the captured piece is added to the value. And finally, if we're in the end game and the piece being moved is a pawn, the value is increased by 1 again. This is to encourage pushing past pawns to eventually be promoted. The sorting helps cut down on time for alpha-beta pruning. If it's already somewhat sorted, then not as many branches have to be visited when searching for the best move. So the next three items are pretty intertwined, so they're sort of difficult to talk about separately, but hopefully I explain it well enough. First is the evaluation function, which evaluates the board that is given. As a note, when I say net value, I mean the value for the white player minus the value for the black player. So the final evaluation is negative. This means that black has the upper hand, and if it's positive, white has the upper hand. So the first thing considered in the evaluation function is net mobility, which is how many moves are available for each player to make. Next, we get the net value of pieces. Each piece has a specific value, and you can see those values on the right. These are standard values for pieces. For this, if a piece existed on the board for a player, its value is added to the player's total piece value. Then we have net control, which is the value of the pieces in the current location. So for example, the queen has a higher control value in the center of the board because it can cover more squares that way, whereas its control is more limited when it's on the edges of the board. And each piece has a different value for each square on the board for each player. Once we get each of these values, then a weighted value is output, which is 0.05 times mobility, since it's the least important, plus 0.1 times control, plus 2 times the piece values, since that's the most important, and these are the values that I found to be the most effective. The next item is caching, which stores the evaluation of boards that have already been seen or evaluated into a hash table. For this, I used Zobrist hashing. With that, there is a random value assigned to each piece for each square on the board at the beginning of the game. And with Zobrist hashing, the hash value does not have to be completely recalculated for each board. Rather, it has to be calculated for the first board, and then we can use the previous board's hash value along with exclusive OR operations to get the new hash value. For my implementation of this, once the hash value is calculated, it is stored in the hash table with the hash value as the key, and the value being the depth of the minimax search tree that this was calculated at, and then the board's value from the evaluation function. When a board configuration is seen while searching and we need to get the board's evaluation, if the hash value is not in the table, then we get the hash, get its value with the evaluation function, and then add it to the table. If the hash value is in the table, then we take a look at the depth. If the stored depth is greater than or equal to the current depth, then we can go ahead and return the stored value for the board. If it's less than the current depth, then we shouldn't use that value because we still need to look ahead, so we continue with minimax normally. So for example, if the board we're currently at is a depth of 3 in the search tree, and the board is cached in the hash table, and the stored depth is 4, then we know that when this board was seen before, it was looking 4 moves ahead. Since that's more than 3, it's safe to say that that's the best value for this board, and we don't need to continue down the search path. If instead the stored depth was 1, that would mean that when the value was stored, we were only looking 1 move ahead, and we still need to search until we get to our maximum depth. In this case, we would also update the hash table entry for this board with its new value and new depth. Next is minimax. This is a way for the AI to make a decision based on the worst case scenario. So for this AI, white is always maximizing and black is always minimizing. When talking about the evaluation function, I mentioned that the net board value is essentially the white score minus the black score. So if the value is positive, white is ahead, and if it's negative, black is ahead. So black is always trying to minimize or go more negative, white is always trying to maximize or go more positive. For finding the best move, it iterates through all available moves and searches through each tree that results from that, and continues until it meets a specific depth. So for beginner, it looks ahead 2 moves, for intermediate 4 moves, and for expert 6 moves. The image here is an example of this. I don't have the time to dig into much more detail here, but this is the core of the chess AI. And here's another image with a better representation of what that looks like in chess. This is essentially the way that the AI sees the minimax search tree, and once we get into higher search depths, the time to take the best move gets exponentially larger. For example, beginner AI doesn't have to search very far down, so the response time is very fast. It only takes a couple seconds. Using the same move, it took the intermediate AI about a minute to respond, and it took the expert AI about 25 minutes to respond. This was with very early moves, and it gets better as the game progresses due to the cached board values, but it is a problem early in the game. So one way to speed up Minimax is to use alpha-beta pruning. This reduces search time by essentially pruning or not searching through branches when we've already found a better move. We know when to prune when beta becomes less than or equal to alpha. Alpha is the best value of the maximizer and begins as negative infinity, and beta is the best value for the minimizer and begins as infinity. You can see in the image here, A is a maximizing node and B and C are minimizing. By the time the search gets to C, A, the maximizer, has a value of 5 from node B. Here, C has a value of 2, and C could search node G, but since C is a minimizer, it's only looking for values less than 2. But A doesn't care how much lower C goes, it knows that B is going to have a higher value than C, which is what A wants. So there's no need to search G, and it can be pruned completely there. So this is a flowchart explaining how all of the elements to work together. I don't have time to go over it, but if you want, you can pause and hopefully get a better idea of it. So here's a demo of me playing as white against the AI on intermediate difficulty playing as black. You can see that in the beginning I am making book moves and the AI is also responding quickly with book moves. And then both of us start taking a little bit longer to make moves. And we don't have to watch the whole thing, but I do end up winning with checkmate, though the AI put up a good fight. So tests were run with search depths of 2, 3, and 4 to see the outcomes as well as the length of the games and cache hits and misses. I ran 5 games for each of the scenarios, and then each of those tests were run 3 times to compare Minimax with alpha-beta pruning alone, then with sorting added, and then with sorting and caching added. So I ran 5 tests for an AI with a depth of 2 versus another AI with a depth of 2 using the base minimax with alpha beta pruning, and then repeated that with sorting implemented, and then repeated that with sorting and hashing implemented. And then I did the same thing with one AI that uses a depth of 2 playing as white versus 3 playing as black, and then repeated the same thing reversed, and then this repeated for the rest of the depths. With all of this, there were a total of 135 tests run. So next I'll go over the results of those tests. First, we have the percent of the scene boards that were cached during the game. This was calculated by recording the boards that were encountered that were already in the cache and the total number of boards that the AI attempted to get from the cache. And then the hits were divided by the total accesses, and that number was multiplied by 100 to get the percentage. So we can see that through all the difficulties, the average amount ranged from about 20% to about 29%. Even though they seem pretty small, with such a large number of boards, this makes a really big difference. For example, with the AI that used a depth of 4 versus a depth of 4, there were on average a total of almost 3.4 million board values that were attempted to be retrieved from the cache, and of those, almost 1 million were in the cache when they were needed. So that means that nearly 1 million times during the game, part of the search tree didn't need to be further traversed, or the evaluation function didn't need to be rerun for those board configurations, and that can make a significant difference on search time. Next, we have the comparisons of the average time to run a game for each grouping using Minimax with alpha beta pruning alone, which is the blue line, then using that with sorting, which is the orange line, and then using both of those with caching, which is the gray line. As you can see, they all sort of start out together for the smaller search depths, though there is still a slight time difference. And if we skip to the end with a depth of 4 versus 4, we really see a big difference. Without sorting or caching, the average game time is a little over 5 hours. Then once the sorting is introduced, that time dips significantly to about 25.5 minutes. Then when caching is added, a few minutes are removed again. So with all of the time-saving changes, the average game time was cut by about 4.5 hours. There are some points here where the time is a little higher with caching implemented. I believe this is due to the AI randomization and not necessarily due to the fault of caching. I also previously stated that the depths used for beginner, intermediate, and expert were 2, 4, and 6, and I'm using 2, 3, and 4 for the tests. That's because to run these tests with a depth of 6 would have taken way too long. So seeing those trend lines is an acceptable way, I believe, of seeing the effectiveness of these implementations. Finally, we have the comparison of the outcomes for each game type. I have these grouped slightly differently. So the first 3 groups we would expect for the most part for there to be no winners since they're evenly matched. However, I will mention that white in chess has an inherent advantage since they play first. So in real games, white does tend to win more often with evenly matched players, and that is taken into consideration with the analysis here. So for each of these, we're looking at games ending with 5-fold repetition, insufficient material, stalemate, white winning, and black winning. In the first 3 groups, all of the bars are fairly close in height, which is what we want. We can see, for example, that out of the 15 depth of 2 versus depth of 2 games, white won 5 and black won 2. So 7 out of the 15 games had a winner and the remaining 8 did not. And out of the games with a winner, white won a little bit more than black, which, as previously explained, is an acceptable outcome. And for the other 2 sets in this grouping, the 3v3 and the 4v4, we see very similar behavior. In the middle grouping of 3 game types, where white had a higher search depth than black, we expect white to win most of the time, and you can see by the yellow bars that that was accomplished. I would be more concerned with the 12 games without winners here if the depths had a bigger difference between them, but with such a small difference in search depth, these are good results. In the final grouping, we expect black to win most of the time, and you can see by the light blue bars that this was accomplished, though not quite as well as in the previous set. Black is still winning most of the time, and white does have an inherent advantage, so I would say these are good numbers, but it is something that I'd like to try and improve in the future. So of course, besides trying to get the AI to be more successful when playing as black, there are updates I would like to make to this in the future that were either outside of the scope of the project or came up too late in the process. Firstly, a better user interface should be added. It should be more interactive with drag and drop pieces rather than typing into the console. There should also be indicators of where the pieces can be moved to, a choice in the UI of playing against the different difficulties, as well as information on how the game ended. Next, to further reduce the search time, I think multi-threading could be introduced. Then the list of moves could be split up into 3 or 4 or 5 chunks and all searched at the same time, which would speed up Minimax search some more. I'd also like to add some variety to the book moves used. Right now, it pretty much always makes the same book move, so the beginning of every AI versus AI game is about the same, and I think some variety to that would be more realistic. Additionally, a beginner AI should maybe sometimes mess up a book move rather than having them all apparently memorized. I'd also like some way to reduce the number of fivefold repetitions. I think they're occurring a little too often right now, and I'd like to implement a way for the AI to avoid that as much as possible, because I think unless they're in a bad situation, most human players would not do that very often. And finally, I'd like the AI to have some sort of understanding of endgame strategies, like specific steps that players know that would result in a checkmate. And this would have to be scaled from beginner to expert to make it appropriate for each difficulty level. And that's everything. I'm sorry for going kind of fast, but there's a lot of information, and thank you for watching.